Alright, see how this works. So I'm trying to write big so that you can actually see it. Hopefully I don't have this camera too high up in the air. So just gotta remember to write big. Basically, there's a couple things we missed in chapter 6. Actually, one thing we missed and one thing I just wanted to remind you of that actually showed up on your test on the bonus. I haven't graded them yet. Well, by the time you guys watch this, I may have, because I'm going to grade them after I make this video here. So, but as of right now, I haven't graded them, so I can't really comment on them. But so here we go. One thing we missed, and like I said, one thing I'll remind you of, and then I'm gonna move on to chapter 7. We will still have a quiz on this piece we missed in chapter 6. It's not much. It's pretty easy. So here we go. I gotta check. Oops, I need to keep the paper up here. All right. Still not very good at this. Okay, so in 6 we did the Riemann sums, right? And we did left, right, midpoint. We did the trapezoid approximations with the Riemann sums. Well, we figured out the trapezoid was most accurate. And if you could imagine, there's a way to be even more accurate than a trapezoid. Think about when we broke it into the trapezoid, we always went like that. And then there was some curve along here. Well, now, what we're going to do, it's basically like the trapezoid, but this piece, instead of being a straight line, is going to be a curved line. And this will be even more accurate. And this can't be just any curved line, it actually has to be a parabola. Hopefully the shadow of my hand isn't too, I don't know, hopefully you can see this. That has to be parabolic. And it turns out, if we do this, not going to do the proof. That would take too long, not that big a deal. Can you see that? I'm just checking to see if you can even see this. All right. Sorry, I'm talking to myself here, literally. So if we do this, if you break the area under your curve into sections, just like before, so there'll be a whole bunch of these, and don't write this part down here that I'm about to write, but so I'm kind of just going to tell you where this comes from, so don't write this part down. I'm always nervous when I do these videos. I don't know why. It's just weird, I guess. So if that's your parabola, turns out, we'll call this side the left, this side the right, and then if you put a line in the middle, call that the middle, and if you call this base, for some reason they call it H, probably because like the height of the trapezoid. Turns out the area, this whole area here, whole thing, the area of that is h over 3 times the height of that line plus 4 times the height of the middle plus the height of the right side. Again, not going to do the proof, and don't write that part down. This is just kind of where it comes from. So the idea here, that's the basic idea, and this has a name. It's called Simpsons rule. Gotta remember to write big here. This is the part you want to write down. I don't know if this was Homer or which one it was, but it's called Simpsons rule. Basically says integral from a to b f of x dx. It's just another way of doing an approximation of a Riemann sum, but it's not left or right or midpoint. It's Simpson's rule. If this is h, and well, I'll do an example, and this will make more sense. it's h over 3 times y0 plus 4 times y1 plus 2 times y2. And these 4's and 2's keep alternating, plus dot dot dot, however many you have. And this is really weird, but we're not going to do the proof, just go with it. 4's and 2's keep alternating until your last one, and then you're done. These y0 is y1, it's basically the heights. So like, if this was h, this would be y0, this would be y1, and then I would have a whole bunch of these, right, depending on how many subdivisions I broke it into. This one would be y2, y3, y4, whatever, how many there are. Just do a quick example, this will make more sense. If I want to use Simpsons rule here to approximate the integral 0 to 2 of 5x to the 4th dx. Directions basically say use Simpsons rule, so use Simpson with n equal to 4. N equal to 4, that's just how many intervals you want to break it up into. And actually, when you do Simpson's rule, your sub-intervals, the sectors you break it into, that has to be an even number. And that has to do with the 4's and the 2's. Don't worry about that. Just, like I said, just go with it. So if we're going to do this, we can think of this just to kind of draw a little sketch of what this would look like. This would be a parabola looking thing, right? X to the 4th. So it would look something like that. If I'm going from 0 to 2, there's 2. Breaking it into 4 sections. So there's 1. Each of them is going to be half, right? So there's 1.5. Here's 0.5. So that's kind of what she would look like. Like that, right? Something like that. Anyway. And I'm actually going to make a table. It'll make this easier. That way I can get these numbers quickly and easily, right? Because I'm going to need all these. These are the y0, y1. That's these. Like this would be y0 would be right here, y1 would be right here, y2, y3, y4. So I'm going to have one. I'm actually going to have 0, 1, 2, 3, 4, 5 of them. All right. So if I do that, make a table. I just got really loud, sorry. Hopefully you don't have your volume up too loud. Make a table here. So when x is 0, 1 half, 1, 3 halves, 2. You can plug that into your calculator, get your table. Plug in 0, right? You know how to make a table. It'll be 0, plug in a half, you'll get 5/16. 405/16, and 80. Maybe the calculator, maybe that's not the best way to go, because I'm pretty sure it'll give you those at decimals, but we want to be exact, as accurate as possible here, so we'll leave them like that. So anyway, the way to set this up, right and big enough. The way to set this up is just go 0 to 2. Right, I'm just going to write the problem. And now I'm going to use the rule. So h over 3. Well, what is h in this case? H is these heights, right? So it's each one is a half, right? So 1 half over 3, that's the same as 1 half divided by 3 is 1/6, right? Y0, so that's just these.